Let us do another derivation, and the final expression is very important for your JEE Main and Advanced, and of course not for your school examination. For JEE Advanced, not for your school examination, and what it is, force between the plates of a capacitor. First case, when a battery is connected. Second case, when a battery is not connected. And third case, when a dielectric is introduced between the plates of the capacitor. To understand that, we need some basic understanding that we studied in our electrostatics lectures. And what understandings are required is the following: is an infinite sheet of charge Q is distributed on it, its area is A. Due to this, either on this side or on this side, say this point, any point, what is the electric field due to this? Means when a test charge was kept here, how much force was experienced by this test charge due to this charge configuration having charge Q distributed on a area A. We had derived here the electric field was sigma by 2 epsilon naught, where sigma is equal to surface charge density was equal to charge over area. Means on A area, the area of this is A. On A area, Q charge was distributed on unit area, the charge distributed is Q by A. This was called sigma, and due to this, on this side the electric field was sigma by 2 epsilon naught. Sigma is equal to Q by A. And if you look at here, this is not depending on distance. Means here the electric field is this much, here also it is the same, here also it is the same, on this side it is also the same. This does not depend on the distance, and it is to this side, because if you keep it 1 unit of positive charge, this will be repelled by this, so it is to this side. Similarly, if the same thing is now negatively charged, having same charge Q but negative, area A, and for this case also the electric field was sigma by 2 epsilon naught to this side, because if you keep a test charge it will be attracted by this, so it is to this side. Sigma was equal to Q over A, where A is the area of each plate. Now one more concept we need to understand. That is the second concept is, suppose there is a charge Q. This is a charge Q. This is kept in the electric field of some other charge. Then this charge was experiencing a force F is equal to the charge of this multiplied by the electric field E of some other charge configuration. So a given charge Q, when placed in an electric field E, the same charge was experiencing a force is equal to QE. This we also know. Now look at these are the two plates, M and N, two plates of a parallel plate capacitor. This has a positive charge Q, this has a negative charge Q. Now let us derive this plate is experiencing how much force. So to find the force on this plate, we have to consider its charge, that is minus Q, and the field of the other plate. Now this plate having area A and having plus charge Q, on this side the electric field will be sigma by 2 epsilon naught, that I just explained, and it will be to this side. Now, so force on this plate will be charge of this plate and the field of this plate, that is QE. Its charge is minus Q, that is minus Q, and the field due to this plate is sigma by 2 epsilon naught, so minus Q sigma by 2 epsilon naught. This negative sign indicates the force on this plate is to this side, that is opposite to the direction of this electric field. Means this being negative, this being positive, this will attract this plate, right? So on this plate N, the force is F is equal to Q sigma by 2 epsilon naught. The negative means to this side. So the negative acts opposite to the direction of E, that is towards the left. Now now sigma is equal to charge over this. So this expression can be modified as, I can write it as minus Q by 2 epsilon naught, and for sigma I can write Q by A. So minus Q into Q square by 2 epsilon naught A. This is the force on plate N having charge minus Q due to the electric field of this plate, that is E is equal to sigma by 2 epsilon naught. Similarly, to find the force on this plate N, M, we have to consider the charge of this plate and the field of this plate. So that is what I am going to show you in the next page. Now look. Now to find the force on plate M, consider the charge on this plate, that is plus Q, and the electric field of this plate. Now since this is negatively charged, and in the first page I explained the field was sigma by 2 epsilon naught, which does not depend on distance, it will be to this side, because if you put a test charge, that will be attracted by this, so it is to this side. So we know F is equal to QE. So force on this plate due to the electric field of this plate will be Q into E. Q of this plate, that is plus Q, and field of this plate, that is sigma by 2 epsilon naught. So that again becomes, for sigma I can put Q by A. So Q into Q becomes Q square. A comes to the denominator, so it becomes 2A epsilon naught, and it is towards right. So on this plate the force is towards right due to the electric field of this plate. So in general, whether it is the plate N or plate M, the force is equal to Q square by 2A epsilon naught. Right? This was the force on this plate, and same was the force on this plate. The negative was indicating to this side, and the positive here is indicating to this side. Right? Now let us convert this Q in terms of capacitance of the capacitor and the potential difference applied across it. How to do that? How to do that? Now look at this page. Now it is the same plate M. This is the same plate N having charge plus Q minus Q. This is connected to a potential difference V. So if a battery is connected, therefore this is constant, V is constant. And we know for a capacitor, charge on each plate Q is equal to C into V. And for a parallel plate capacitor, M and N having a distance D between the plates, your capacitance was epsilon naught A over D. This was derived in the electrostatics lectures while deriving the capacitance of a parallel plate capacitor. And we have just derived force on each plate is equal to Q square by 2A epsilon naught. So for Q I can substitute CV. So for Q I substitute CV, square of that by 2A epsilon naught. So this becomes C square, this becomes V square by 2A epsilon naught. Now for C I will put epsilon naught A over D. So for C, when I put epsilon naught A over D, which is the capacitance of a parallel plate capacitor, for C I write epsilon naught A over D, square of that V square over 2A epsilon naught. So epsilon naught square, A square, V square, D square. D square comes to the denominator, 2A epsilon naught. Now 1 epsilon cancels, 1A cancels. So your force becomes, I am left with epsilon, I am left with 1A, where A is the area of each plate, V square divided by 2D square. Now look, what are constants here? Epsilon naught is constant, area of the plate is constant, the V is constant, the battery is connected. So it is the distance D square. Means when the battery is connected, if I take this plate to this side and this plate to this side, then the distance D increases. Or if I bring the two plates nearer, the distance D decreases. So D is in the denominator. So F is proportional to 1 by D square. So if D increases, that is if you separate the plates away from each other, D increases, therefore force decreases. If you bring the plates close together, that is D decreases, therefore F increases, right? So this expression you cannot of course derive while solving the numerical, so you have to remember this expression. Here also you can make some changes, that is epsilon naught A over 2 V over D whole square, and potential divided by distance is electric field, means you can write it as, for this you can write E square by 2, and depending on the situation. Now if battery is not connected, now this was the force we had derived on each plate, Q square over 2A epsilon naught on each plate, means first the battery is connected, so the two plates are charged, then the battery is removed, means the charge on the plates remains constant, so Q remains constant, Q constant, Q square constant, 2 constant, A constant, area of each plate epsilon naught is constant. So there is no expression, there is no D here, that is the distance between the plates. So in this case, when the battery is not connected, whether you bring the plates nearer or take the plates away from each other, the force does not change, that remains constant. So does not depend on D, that is since Q is constant. Now if a dielectric is introduced, in electrostatics chapter we learned the capacitance C of a parallel plate capacitor was equal to epsilon naught A over D, and when a dielectric was fully introduced, the capacitance was becoming K times C. So C, that is epsilon naught A over D, becomes K times epsilon naught over D. Now the force that we calculated here as here epsilon naught A over D whole square, if a dielectric is kept, we should put a K here, K square. So a new term will be introduced, K square, for a dielectric. So your F becomes K square epsilon naught A V square over 2 D square. So now that is equal to 2 D square. So that is equal to K square epsilon naught A over 2 that is equal to epsilon naught. So you can write it here, a new term K will be introduced here. So K epsilon naught AV square, K epsilon naught AV square by 2D square. So this is the force if a dielectric is introduced. So you can change it as since potential divided by distance is equal to your electric field, so you can write it as K square epsilon naught A over 2 V square by D square, that is same thing as E square. So this is the force on each plate if a dielectric is introduced.